Right, so for an acid-base titration, you're going to be expected to do the primary combinations are strong acid, strong base. That's the most common one that you'll see. You'll also see strong acid, weak base, or strong base, weak acid. So those three combinations you're going to work with. You will not have to do a weak acid, weak base combination because those combinations are unexpected where their equivalence points actually going to wind up. And an example of some types of questions you'll be asked. So you'll be asked how much to reach equivalence. That's just basic stoichiometry, right? So this right here is just stoichiometry. pH after a certain amount of something has been added. So again, this is stoichiometry with a pH calculation, right? So this is stoichiometry plus pH. May involve Ka, Kb, or Henderson-Hasselbalch. So you may have to use one of those to figure it out. The pH at equivalence point, and again, I'll show you how to calculate that a bit later. Which indicator you want to use. There are a bunch of different chemical indicators that you can use for this. And how to find pKa or pKb from the lab data. This is actually a really easy thing that is extremely important when you do calculations, and everyone always overlooks this. Right, so we'll start off with the basic combination, which is the strong acid, strong base. What you see on the right is what's called a titration curve. The titration curve is the pH of the solution after a certain amount of something has been added. In this case, we're starting off with HCl in our flask, and we're adding NaOH from the burette. And as we add NaOH, since it's basic, the pH will increase as we keep adding. Right, so the pH will increase fairly slowly as you get closer to equivalence. Because again, remember, pH is a logarithmic scale, so it's going to increase, but it'll increase at a very gradual pace. Once you get close to equivalence, you're going to see a spike. And afterwards, you're going to see the pH level off because, again, you're adding more base, but you're also adding volume, and the logarithmic feature of pH kind of makes it level off after a little while. The key thing here is that for a strong acid, strong base, the equivalence pH is always going to be 7, right? So equivalence pH is 7 for any strong acid, strong base combination. And why is it 7? Well, let's look at our HCl and NaOH, right? So HCl plus NaOH will form sodium chloride plus water, or for our net ionic equation, H plus OH minus yields H2O. Right? We have a strong acid with a strong base, which means that the salt that we produce is going to be a neutral salt, so the pH of this salt will be 7 at equivalence. So that's the easy way to tell. Find out where the pH is 7. If you don't have good enough graphing data, what you wind up doing is if you see where the rise starts, so if you see like the rise, so here and here kind of, just shoot for the middle of where it's rising. Right, so that's the easy way to do it. Strong acid, strong base are easy though. Now if we do weak strong combinations, so this is going to be a weak acid, strong base. You can also do strong acid with a weak base. Right, and that's just going to be modifying what I'm going to tell you here a little bit. Now notice that there are a couple of differences in the titration curve. So let me go back for a second. So look at this titration curve. Now look at this one. Notice there are a bunch of differences in this curve. The first thing that you should note, well, the first couple of things you should notice differently. First, initial pH is usually going to be a little bit higher. Now, that's not to say this will always be the case, but remember that for the same concentration, a weak acid will have a higher pH than a strong acid. It is possible, though, based on concentrations for the two numbers to be the same. But this is generally the first indication that you have a weak acid is a higher pH. The second indication is what we call the buffer region. The buffer region is the point from here to here, right? So this is our buffer region. The reason why is because as we start adding in our base, we now have our weak acid, right? So we now have HA, and we're adding in our base, so now we have HA, and we have some A minus, which is our conjugate base, right? So now we have HA and A minus. So we have a buffer right here. Once we get to equivalence, at equivalence, we no longer have any of the weak acid. We've reacted all of it. All we have here is just the basic ion. And here we have the basic ion and extra hydroxide. Right, so these are the ions that we'd have present in solution. Because we're working with a weak acid strong base, so weak acid strong base will make a basic salt. Basic salts have a pH above 7, so our equivalence pH is going to be above 7. Now, if you're going to be asked to find the pH at equivalence, what you do is you're going to use a pKb problem. Right, so if I give you the Ka of the acid, you find the Kb, and then you use that to go in and find the concentrations of everything involved. Right, and we'll do some practice math with that a little bit later on. The key feature of this graph is that you can find pKa from this graph directly. What you're looking for is you're looking for half the equivalence volume. Right, so here, this equivalence is at 25. What I would do is I'd take half equivalence, or 12.5 mLs. The pH at this point is equal to the pKa. The reason why is because at this point I've added exactly half of the base that I need to titrate. So I have an equal number of moles of weak acid and our conjugate base, right? So if you remember Henderson-Hasselbalch, pH equals pKa plus log of base over acid. Here, since base equals acid, this right here is going to be pH equals pKa plus log of 1. Log of 1 is 0. So pH is equal to pKa. So you can find the Ka of an acid from this graph. Just go to half equivalence, that tells you the pKa, then undo the negative log, and that tells you the Ka. And when you're going to be asked to do this, if you're asked to do this by looking at the graph, you're going to get some leeway, so don't worry too much about it being exact. You'll get a little plus or minus. Right, so this is working with a weak acid and a strong base. If you were working with a strong acid and a weak base, this graph would look kind of opposite. Right, so if we're working with a strong acid, and I'm actually going to change my color here. If we're working with a weak acid and a strong base, we're going to start off like this. Right, so again, our equivalence pH is going to be below 7. We start off, we have the same buffer region at the beginning. We hit equivalence, and then it levels off towards the end. And the math would just be the opposite of what you see here. At half equivalence, pH would be pKb. Right, so pH equals pKb at half equivalence, because this is a weak base strong acid combination. Right, and here this would be a pKa problem because this salt is slightly acidic. Right, so that's how the math would work for this. Now, there are a bunch of different ways that you can find equivalence. The first way to find equivalence is if you're using a pH probe. You look for the inflection point. Now, the inflection point was where you had that huge jump, so the center of that huge jump on your graph, or when we do this with the actual pH probes on Vernier software, you're going to look for the second derivative, because the inflection point is defined as when the second derivative is 0, so when it changes concavity, so it'll go from plus to minus, or from minus to plus. It's when it passes through that 0 point. The other way you can find equivalence, and this is what most titrations wind up doing, is they use a pH indicator. A pH indicator is just something that'll change color at the equivalence point or fairly close to it. If you choose it properly, you can choose an indicator whose pKa is the same as the pKa of the salt that you're working with. All right, so for an indicator, again, these are different molecules. So the molecules have two different forms. You have the acidic form and you have the basic form. So if your pH is less than pKa, right, so here, pH is less than pKa, we're going to have the acidic form of this molecule. Right, the pH is too low for this molecule to want to donate a proton. It has an excess here, right? So remember Le Chatelier's principle. If pH is low, we have a very large H plus concentration. It's going to shift this reaction to the left towards this side. The basic side is when you have pH greater than pKa, because now we have a deficit of H plus, which means that the reaction is going to proceed forward to produce more of it. The key thing about these is that these two different forms have different colors. Right, so for example, if I take phenolphthalein, so for pheno, the acidic form of pheno is clear or colorless. The basic form of pheno is pink. This occurs at around pH of 8 to 10 is when this transition occurs. Now the difference between a pH of 8 to 10 usually is like 1, maybe 2 drops. So it's not going to be that large of a difference in number of moles given to you. And again, key thing is choose the indicator whose pKa is closest to the equivalence pH that you're expecting. And my last slide is basically just a bunch of different indicators that you can choose and their pH ranges. Right, so for example, again, phenolphthalein, colorless to reddish pink, happens between 8 and 10. So this is a very good indicator to use. So phenolphthalein is what we're going to use typically for strong acid, strong base titration, as well as weak acid, strong base titrations. Right, because again, 1 or 2 drops will get you from colorless to red. If you were working with, say, strong acid and a weak base, I'd want something that changes a little bit under 7. So I'd be looking probably somewhere in the ballpark of, depending on how acidic the salt is, somewhere between methyl red and bromothymol blue. Right, so these would be good for strong acid, weak base titrations. Thymol blue is actually an interesting one. Thymol blue is nice for polyprotic acids, right? Because what happens here is you have the first indicator color change at a pH of 1 to 2. So when you lose the first proton, it changes from red to yellow. Then when you lose the second proton, it'll change from yellow to blue. So that's what that's fairly good for. All right, so these are some indicators you use. The way it'll basically work is I'll give you an indicator. I'll either give you its pKa or its pH change range, and you would pick whichever one is most appropriate given the titration that you're doing. All right, so that's it for notes. Come back for the problems if you want to see any of those done out.